Hello friends, welcome to Alsi Coder. We often see that people struggle to solve recursive problems, right? Problems on recursion. So today we will try to see how recursion actually works. Because most of us, what we do is we just memorize the terms. Like for say, if we are asked to find a factorial of a given n, what we have memorized from our childhood that it is n into factorial of n minus 1, right? But today we will try to see the intuition behind this, how and why this works. Okay, so this is directly linked to PMI, the concept of principle of mathematical induction, right? So, what is it? So, for any given f of n, for say we need to prove that f of n is true for given set of natural numbers. We need to prove it. So, what are the steps to prove that a given fn is true for all set of natural numbers? For say, so the given steps are the first step that we need to do is we need to think about a base case, right? Which says that if you recall the principle of mathematical inductions, you need to prove that f of 0 is true, right? F of 0 is true, right? Then the next step is step 2 is the induction hypothesis, right? Induction induction hypothesis, right? So in induction hypothesis we assume that, okay, we assume that f of k is true, okay, we assume that f of k is true, and the next step is induction step where we have to prove that f of k plus 1 is true, right? So we need to prove that f of k plus 1 is true. So if somehow we prove that f of k plus 1 is true, we can say that f of n is true. This is what the PMI or principle of mathematical induction tells us. So let us move on to an example to understand how it works. For say, summation of first and natural numbers is n into n plus 1 by 2. We all know this, right? And we need to prove it, right? Okay, so what we will do, we'll first we'll follow the first step, that is proof for f of 0 it is true. So the LHS is summation of first 0 terms, that is 0, and RHS is 0 into 0 plus 1, that is 0 into 1, 0 by 2, 0. So we prove that the first step holds good, right? Now moving on to the next step, we will assume that f of k is true, right? That is summation of k. So we'll replace n with k, right? K into k plus 1 by 2 is true. We assume it, I'm stressing again, we assume it in the induction step, induction hypothesis, right? That this holds true. So if somehow we can prove summation of k plus 1 is f of k plus 1 is true, then we can say f of n also holds true, right? So we can say summation of k plus 1 is equal to summation of plus k plus 1, right? So k plus 1th term and then the summation of the previous sum, right? So we can replace summation of k with the previous induction hypothesis. So this is equal to k into k plus 1 by 2 plus k plus 1, right? So we will multiply, let's multiply it by 2 and divide it by 2. We can do that, right? We are not changing anything, correct? So now let's take common k plus 1 by 2. So we are left with k plus 2. So if you see properly, have we proved that k plus 1 is true? So put k plus 1 in place of k. So it's k plus 1 into k plus 1 plus 1 k plus 2 upon 2. So we have proved that k plus 1 holds true. So we can say that f of n or summation of n, that is n into n plus 1 divided by 2, holds true, right? So recursion works in the same way. We generally overcomplicate ourselves by going deep dive into the recursive calls. For say, I see students struggle. For say, they are given some to find a factorial of a given integer n. So they try to deep dive into factorial of n minus 1, then factorial of n minus 2, and then this loop continues and they get stuck. So we have to, for every recursive problem, you just need to think of the PMI approach. Okay, you just need to solve a small problem. Okay, just solve the small problem. I repeat, just solve the small problem and assume that in the recursion hypothesis, in the recursion hypothesis, PMI will solve the larger problem. Okay, so let's try to think about finding factorial of a number in terms of PMI. Okay, so for say you are given factorial of n. Okay, so what will you tell? Hey recursion, I know my answer. Okay, for say you are given factorial 4. Okay, so you will tell, hey recursion, I just know my answer. My answer is 4, right? I don't know f of n minus 1, right? I know that my answer is 4. You give me f of n minus 1. So we already proved that f of k holds true. We can prove f of k plus 1 true, right? So let's assume k is equal to n minus 1. So by the induction hypothesis, this will be true. And if k is true, we can prove f of k plus 1, that is f of n, is true, right? So if this is true, we can solve the larger problem. So we'll just call the recursion with the hypothesis. And once we get the answer from recursive hypothesis or the recursion leap of faith, right? So we'll tell, hey, I'll just multiply my answer with the recursive hypothesis, the answer that it gives. I'll give the answer, right? So this is how we solve a problem. For say we have to find factorial. Let's write it on a IntelliJ and see how we can solve a recursive problem. So let's write the factorial program. Okay, factorial, factorial, factorial. Okay, so what are the steps? First step is we identify the base condition, right? That is solve for f of 0. Next is induction hypothesis. So what it is, I will not solve the larger problem. The larger problem, I will give it to recursion or the induction hypothesis. Larger problem will be solved by induction hypothesis. So what will I do? I am a smart coder, right? So I'll do, or we will solve a small problem only. Small problem is easier to solve, right? So we will solve only the small problem as smart coders, right? and then we will return the answer to the larger problem. Correct? So let's write. So we'll write the f of 0 is true, right? We know the value of factorial 0, right? That is f of 0. So if n equal to 0, we will return 1. Factorial of 0 is 1. Else, what will we do? We will define a larger problem, right? Larger problem. Larger problem is factorial n minus 1. So we don't know what is the solution or how n minus 1 will be taken care, right? So we will give it to induction hypothesis. Hey hypothesis, induction hypothesis, I trust you. Hypothesis, hey induction hypothesis, I trust you. Solve the problem for me. I don't know how to solve it. Solve for me. I just know how we can solve the small problem for us, right? So long, smaller problem or the smaller answer. So we can, yeah, smaller answer. We know for factorial and we know the smaller answer is n, right? So guys, for every recursive question, just try to come up with the induction hypothesis, right? You just solve the smaller problem, small, and get the smaller answer. And once we get the smaller answer and we get the answer from the recursion or induction hypothesis, we just return the small answer into a larger problem that we did not solve. We let recursion solve it. Isn't it awesome and magical? It seems right. So trust me, every recursion problem you'll be able to tackle it with ease if you know how to get onto the induction hypothesis that we won't solve. This is the magic of recursion. Recursion will solve it for us. Let's try to run it and see. For n is equal to 4, it should give 24, correct? So let's see. So it indeed gives us 24. So see how easily we solved a recursive problem. We just solve the base case and we just solve the small answer that we know is easy to compute for us, and let recursion or the induction hypothesis solve the larger or the difficult problem. So trust me guys, using this approach we can solve any recursive question with ease and you won't struggle. So in the successive videos, I'll create a series on recursion and will solve tough and complex problem using just this induction hypothesis. Thanks for watching the video. If you see value in my tutorials that I've created, do like, share and subscribe. We'll meet in the next video. Thank you.